welcome you all. In my today's session, I am going to explain serial communication, how 8051 performs serial communication. But before that, I like to share fundamentals of serial communication. So what is a serial communication? In serial communication, n-bit information is transferred from one place to another place using a single data line. So whether the data is 8-bit, 16-bit, 32-bit or 64-bit, entire frame of data will be transferred through a single conductor. So this is the advantage of serial conductor, that in parallel communication, number of conductors are directly proportional to number of bits. If 8 bits are supposed to be transferred, then 8 conductors are required. So if number of bits will increase, number of conductors will increase. However, in serial communication, number of data line remains one irrespective of size of data. This is the biggest advantage, and that is why serial communication has taken over a parallel communication. It reduces the size of the hardware. It makes the it makes the addressing it makes the addressing independent of hardware, but it is at the cost of speed. In parallel communication, all 8 bits will reach from one place to another place at one instead of time. However, in serial communication, data is transferred bit by bit, so 8-bit information will be transferred in 8 time slots. That is the speed of serial communication. We are going to see the unit of serial communication, baud rate. So UART, special IC such as Universal Asynchronous Receiver Transmitter, which consists of universal shift register, is used as parallel in serial out shift register to transfer 8-bit data serially, and as serial in parallel out shift register to convert serially received data into 8-bit parallel form. So what is parallel in serial out and serial in parallel out shift register? Shift register consists of flip-flops. I have shown you 3-bit shift register. So these are the 3 D-type flip-flop. So input is latch when a clock is applied. Here clock is common to all the 3 flip-flops. So one clock, all 3 flip-flop will receive the clock and input will be latch at their output. Let us assume a bit appears, then there is a clock. Whenever there is a bit, there is a clock. So first bit arrives, the first clock is applied. So this input is transferred at the output of first flip-flop. And what is the important thing is this output is input to second flip-flop. So first bit now becomes the input to second flip-flop. Now assume second bit arrives. Then again there is a clock. So now what will happen? First bit which was input will be transferred at the output of second flip-flop, and that is the input to third flip-flop also. So first bit reaches the input of third flip-flop and second is latched, second reaches the input of second flip-flop. Now assume third bit arrives. Again there is a clock. Now what will happen? First bit which was input to third flip-flop will appear at its output. Second bit which was input to second flip-flop will appear at its output, and the third bit will appear at the output of third flip-flop. So what will happen now? All the 3 outputs are available, and this is available in parallel form. So I have received data serially and converted into parallel form. This is called as serial in parallel out shift register. If your data size is 8 bit, 8 such D-type flip-flops will be required. Now, parallel in serial out shift register. Previously, we have seen how input is received. Now, we will see how input is transferred. So, it consists of multiplexer, 2 raised to 1 multiplexer. This is channel 1, this is channel 2. So, PA, PB, PC are the 3 bits. The parallel input. Now, I will transfer it serially. Initially, multiplexer select the channel number 2, so PA appears at the input of third flip-flop, PB appears at the input of second flip-flop, and PC appears at the input of third flip-flop. Now I give a clock. What will happen? PA will be transferred at the output of first flip-flop and it will be transferred serially. Then what will happen? PB, which was input, will appear at its output, and this will appear at the first input of multiplexer. Then PC, which was input, will appear at its output and it will again appear at the channel number 1 of multiplexer. Now multiplexer will change its selection from channel 2 to channel 1. Now I give a second clock. What will happen? This 1 is latched and previously there was PC. So PC was input to second flip-flop because channel 1 is selected. So clock, it will be transferred at its output. So PB appears at the output of second flip-flop and PC appears at the output of third flip-flop. Now I give a second clock. Now what will happen? PB, which was appearing at the output of second flip-flop and the input of third flip-flop, will appear at the output of third flip-flop and it will be transferred serially. PC, which was appearing at the input of second flip-flop, will appear at the output of second flip-flop. So 2 bits are transferred in 2 clocks. Now I give third clock. Then what will happen? PC, which was appearing at the output of second and the input of third, will again be transferred serially. So 3 clocks, 3 bits are transferred serially. So this is how we transfer data serially. We give data in parallel form and using shift register will transfer it serially. So this is how parallel in serial out shift register works to transfer 8-bit data serially. Now it is baud rate. In a serial communication, n-bit data is transferred bit by bit through single data line. The number of bits transferred per second is called as baud rate and it decides its rate of transmission. So number of bits transferred per second is called as baud rate and it decides its rate of transmission. So if I say baud rate is 9600, it means 9600 bits are transferred per second. Now let us see how in 8051 baud rate is set. Now to transfer a bit, timer overflow. Whenever timer will overflow, a bit will be transferred. Now in serial communication, timer 1 is used. Whenever timer 1 will overflow, a bit will be transferred. And timer 1 is used in mode 2. What is mode 2? 8-bit auto reload. Maximum count is 255 and whenever timer will overflow, automatically TH value will be transferred into TL and again second counting will start. So TH holds a starting value of count and TL holds the running value of count. So whenever there is a clock, TL content will change, TH remains unchanged. Whenever TL will overflow, TH content is automatically transferred into TL and counting will again start from the initial value and this is called as auto reload. In 16-bit mode, we used to write TL and TH every time. Here it will be done automatically. So mode 2 is 8-bit, maximum count is 255 and it is auto reload. Whenever timer will overflow, TH value will be automatically transferred into TL. So let us find out TH value for the given baud rate. Suppose the baud rate I want to set is 9600. So it means my timer should also overflow 9600 times in 1 second. So it is a continuous process, which means I need continuous clock. And a continuous clock is generated by an oscillator. So timer is running through an oscillator which having a frequency 11.0592 megahertz. Why this such an odd figure? 11.0592. Why not 12 megahertz or 11 megahertz? The reason is IBM PC has some baud rates 2400, 4800, 9600, etc. etc. So PC has to communicate. So I want to communicate with IBM PC. So to set this baud rate, when I use this crystal oscillator 11.0592, I get a rounded value. I get a rounded value. If I don't get a rounded value, suppose I get 3.45, so I will round it off to 3. So there is a deviation from the actual value. 3.4 को हमने 3 पे shift किया. So there is a deviation from 3.4 to 3. So there is a loss of value. So it creates some error in the serial communication. Baud rate should be matched. Number of bits transferred between transmitter and receiver should match. So the rounded values are required. That is why such an odd value is used. This odd value will always give you a rounded value for your IBM PC selected baud rate. Now we know that oscillator frequency is divided by 12, and that is the operating frequency of microcontroller. So 921.6 kilohertz is the operating frequency of microcontroller. Now UART comes into picture. UART will divide this frequency either by 16 or 32. We will see what is 32 and 16 in a later stage. We assume here that it will be divided by 32. So the frequency becomes 28.8 kilohertz, which means 28,800 hertz. Now, timer is running through a oscillator, and timer is operating at a frequency of 28,800 hertz, and I want 9600 as the baud rate. So timer will convert. The timer will act as the frequency divider here. Timer having an input frequency of 28,800 hertz, and we want output frequency as 9600 hertz. So number of clocks required. So 28,800 divided by 9600 gives you 3. So timer will overflow after every 3 clocks. Timer will overflow after every 3 clocks, so that output frequency is 9600 hertz, which is the baud rate. So to count 3, we know that timer is used in mode 2, maximum count is 255. So 255 minus 3 plus 1, we know this why we have added 1, because 255 timer will not overflow. 255 will receive another clock, then timer will overflow. So if I do not add this clock, so what will happen? 255 minus 3 will be 252. So timer will overflow after 4 clocks. So I am dividing by 4, so baud rate will be different. That is why this 1 is added. So I am subtracting from 256. 256 minus 3. So my count value is 253. Now after 2 clocks it will reach 255, and the third clock will cause it to overflow. So I am counting 3 clocks. So output frequency will come out to 9600 hertz, and which is the required baud rate. So here we have determined the TH1 value FDH. So every time when timer will overflow, TH value will automatically be loaded into TL, and counting will start from FD, and after every 3 clock timer will overflow, so that in 1 second it overflows 9600 times. So timer is acting as a frequency divider here. So this is how we set the baud rate. First divide the oscillator frequency by 12, then divide it by 32, then divide the output frequency of UART by the required baud rate, you will get the count. Then subtract it from 256, you get the count value, TH1. Now there are two types of serial communication: asynchronous serial communication and synchronous serial communication. In asynchronous serial communication, transmitter and receiver both are operating at same baud rate. Before communication, we set them to operate at same baud rate. Both are having their own frequency source oscillator, which may have same frequency or different frequency. In communication channel, we have only data lines. No clock line is there to synchronize the transmitter and receiver. That is why they must be synchronized to same baud rate before communication. We transmit or receive only data. No clock is shared to synchronize the communication. So synchronization of transmitter and receiver before communication is essential in asynchronous serial communication. So in this mode of serial communication, transmitter and receiver are synchronized to same baud rate before data transmission. Both transmitter and receiver have their own frequency source, crystal oscillator, which can be of same or different frequency. Transmission channel consists of data link to transmit or receive data serially, no separate link to transmit clock to synchronize transmitter and receiver. However, in synchronous serial communication, we can see here communication channel have two lines. One is data line and other is clock line. So whenever whenever data is transferred through data line, there is a clock from master. So whenever there is a data on data line, there is a clock on clock line. So clock synchronizes the serial communication. So here we don't need to synchronize the transmitter and receiver to same baud rate before communication, because whenever there is a data there is a clock, so clock line automatically synchronizes the communication. So in this mode of serial communication, communication channel consists of data line and clock line. Data is transferred through data line and it is synchronized through a clock on clock line. Master generates a clock for every bit of data transmission. There is thus no synchronization is required prior to transmission. Now in my next lecture, I will explain you serial control resistor. This resistor is used to control the serial communication. I will explain this in my next lecture. So I hope you have liked this serial communication session. If you like it, to please press the like button and share with your friends also. And do subscribe my channel so that when I upload new video, you will be intimated. Thank you. Thank you.